Good morning. Okay, so let's begin with the new topic today. This is on radiative heat transfer or radiation in short. So, when we discussed radiation in the first lecture, where I just sort of introduced a few ideas there, I said that this is one mode of heat transfer that requires no medium and it is relevant to many industrial processes that we see around. So, it's relevant to anything which requires, let's say, fossil fuel combustion because the temperatures there are high, and primarily the mode of heat transfer is actually radiation. It is also relevant to in the present day and time, a lot of emphasis is placed on clean energy and solar energy. So it is also relevant to solar radiation, how we capture solar radiation or how we use it for energy conversion. So these are some of the common reasons why we will actually study this topic in some detail in this course. Now, we'll specifically deal with thermal radiation. There are radiations of different types, but we'll talk about thermal radiation. And thermal radiation is basically associated with the energy which is emitted as a result of a body's finite temperature. So, any matter which has finite temperature, which would mean that it's more than 0 Kelvin. So, any matter at finite temperature will emit radiation. So we'll look at these scenarios, and as a simple thought example, and some of you may be familiar with this. So let's say we have a large enclosure which I'm going to call as surroundings. Okay, so maybe there we have a large enclosure which could be a cavity or some box. So this is an enclosure, let's say, which has some temperature, let's say T surrounding. Okay, and say I put a body inside this enclosure, a solid, which is at some temperature, let's say Ts, and let's say Ts is more than T surroundings, and the medium inside is vacuum, so there is no possibility of conduction or convection in this system. So we know that from measurements we know that the solid cools down and eventually attains the surrounding temperature. But since, as I said, we don't have any medium, so there must be some form of energy exchange, and that is what we're going to try and study. We are going to study this form of surface emission or exchange of emission because of radiation. Okay, now there is one more sort of simplification that we will make in this course, and that is regarding specific form of radiation. Typically, radiation, I mean, if you read any graduate level textbook, you will realize that radiation is actually something that every body emits because of its finite temperature, but also it is actually a bulk process. That means that the volume, it's a volumetric phenomena, so every molecule inside the body will actually be emitting. But typically in solids, especially what I'm going to call as opaque solids, we can consider the radiation to be a surface phenomena. And what we can assume is that a thin layer at the surface, which is about a micron in thickness, is what really radiates energy outside. So you don't see radiation from internal matter reaching out. That gets absorbed internally only, but then it's the outer layer, which is roughly maybe 1 micron, but for practical purposes for us, it is basically the surface itself, which is going to be radiating. So we will consider radiation in this course to be a surface phenomena. Okay. So that is one simplification that we're dealing with in this case. Volumetric phenomena typically happens when you are dealing with gases, and absorption or radiation or emission. There is a slightly more complicated thing which I'm not going to cover in this first course on heat transfer. Now, radiation, it's easy to tackle radiation by using some fundamental concepts. And so the way to go about studying radiation is by saying that radiation has wave-like properties. So there is a wave nature associated with radiation, which means that we can use wave properties to quantify characteristics of radiation. So we can use wavelength as one parameter, and wavelength can then be written in terms of the frequency. So typically we use the standard equation, which is standard, which is an equation which relates wave properties, the wavelength and the frequency. So this is something that we'll commonly use, except you will see now that it is more common to report wavelength properties in terms of, or rather, radiation properties in terms of wavelength only. Frequency is very, very rarely used. So wavelength typically would be reported in microns, and you'll see why. And frequency, of course, is in hertz. And c is the speed of light in that medium, and we know that speed of light in vacuum is 2.998 10 to the power 8 meter per second. This is the speed of light in the medium. Okay, now let me just bring in the spectrum of electromagnetic radiation that we will generally be concerned with this in this course. So let me just bring that picture here. So this basically shows a spectrum of electromagnetic radiation that we will be dealing with. As I said, we will be dealing with thermal radiation. So that is, a narrow band here which is shown, which is going to consider thermal radiation. So it takes into account some part of ultraviolet radiation, all of the visible spectrum, and the infrared spectrum. So if you see that infrared is also there. So why do we call this as thermal radiation? So this I don't want to answer right now. Maybe you will guess by the next lecture why we call this as thermal radiation. Although you have done, I'm sure you've done this in. You're aware of this spectrum, and you are aware of one key law that I'm going to use. That you can use to justify why thermal radiation. Okay, so 0.1 microns to 100 microns is what would be of great interest to us in this course, which is going to be the part of thermal radiation that we are going to tackle. Now, before we move forward, there is some, before we actually do any detailed calculation or any detailed design based on radiation properties, uh, one of the important things is to actually lay down the background of radiation. And to start looking at the background, we need to first define some very basic terminology. So I'm going to use today's lecture to actually define some terminology which is not very easy at first sight, but as you go along, I think it would become easier to understand what we're doing. So the first thing that I want to discuss is is that radiation, which is wavelength dependent, has a specific name for it, or you will see that we will use a specific name every time we talk about radiation which has a wavelength dependence. So if I plot, let's say, radiation on the y-axis and wavelength on the x-axis, and I'm saying radiation very loosely now, what I'm going to be doing is plotting some kind of radiation intensity, which we'll come to very soon. So let's say we have some quantifiable measure of radiation on the y-axis, wavelength on the x-axis, and maybe the radiation depends on the wavelength in some form. Okay. So a variation, when you have the magnitude of radiation changing with wavelength, or when it varies with wavelength, we call this as a spectral distribution. So spectral is the key word here. That spectral would actually imply that you have radiation which is a function of wavelength. The second aspect would be, let's say, if you have radiation when plotted as a function of some direction. So typically in radiation analysis, we deal with spherical coordinates, and I'll show you why. But so let's say we deal with the zenith angle, which is theta. Okay, this is, let me say, is the direction. So theta was at zenith angle, which is measured from, let's say, the z-axis, if you remember a little bit from spherical coordinates. So if the radiation intensity, let's say, depends on the wavelength or the direction, then we call this as a directional or a directional distribution. So when the radiation basically means that when you're looking at radiation from different angles, you get some dependence. Okay, so that is one other aspect that we will be concerned with, and quite heavily. In fact, both spectral and directional dependencies will be very, very heavily used when you talk about radiation. The third, I should not say terminology, but I think I would introduce that as a variable that we will tackle is called as solid angle, which is typically denoted by the symbol omega. So solid angle is very similar to angle in a plane between two rays. So for instance, let's say we have some origin and I have a small arc in a circle, and I'm going to draw it exaggerated. So let's say we have a small arc in a circle which is of length, let's say dl, and the distance is, let's say, r from the center. So in a plane, when we talk about this angle, which I can maybe write as d alpha, in a plane we can write d alpha is dl by r, right? That is the angle in a plane, which is the angle subtended by two rays in a plane. And we know that this d alpha has units of radians. Similar to this, a solid angle is when you look at some area. Okay, let's say this is the area that I'm going to deal with. Let's say DAN. I look at some area and I look at the angle subtended by this area. And the angle subtended by this area would actually be not simple. It's not an area in the plane. It's an area. So basically, it's a plane in itself. So the angle would be this kind of, if you can think of it, an arc or a circular, if I can say loosely, a curvilinear angle. So this angle is defined as d omega. And let's say with the distance again, if I say that this distance is r, then we define solid angle d omega as DAN by r square. So the area by the distance square. The units of this angle are steradians, sometimes written as SR.
Sir,
Yeah.
sir, this d omega is not clear, sir. Can you please explain?
So I'm saying that, let's say you have a surface, right? You have a surface and you are looking at that surface from some point in space. Okay. So if I can draw rays from that point which span the entire circumference, or rather the entire periphery of that area. Okay, if I draw rays from that point which span the periphery of that area, then the angle in that plane, the angle covered by those rays, is what is going to be called as a solid angle. So think about it, a three-dimensional object, not a two-dimensional. An arc is a two-dimensional object. Three-dimensional would mean that you are looking at an area and you're trying to see, from a distance, what is the area in that region, which you are using to see that object. Does it? I don't know. Maybe it's not going to be easy to explain it without anything. I don't know. How do I show it otherwise? Does it make any sense? Or imagine a three-dimensional object. Okay, let's say we have a three-dimensional object. I have this three-dimensional object. Okay, when you look at it from your end, you can say that from starting from a point, you have rays which cover the entire periphery. So the angle, when you take these rays to that point, the angle which is subtended by those rays is actually what is a solid angle. Do you understand? Is that a better explanation? I don't know. Whoever asked that question.
I think so it's need. I will search on.
It's not about. So do you see that the three-dimensional object will not have a plane angle like d alpha, like the way I've drawn it? A planar
Yes, sir,
surface,
yes.
a planar surface will not give you an arc like this, right? It is actually a surface itself. So when you are looking at a surface, you are now looking at an angle in three-dimensional plane. It's not an angle which is d alpha, which is in a line, or in a 2D plane. Now you're looking at three-dimensional object.
So, sir, can I say that about d alpha, that it's a circle which when the d alpha grows, then the radius of that circle increases.
Then sorry, what are you saying? When d alpha?
When d alpha get bigger, then the solid angle become bigger. Like
No, no,
it's
no,
like
no,
a
no, no, no,
circle.
no, no. We're not. No, no, you're not. So d alpha, you can imagine, yeah, it is part of an arc of a circle. That is right. D alpha. But
Yes.
d omega is not related to a circle. D omega can be imagined to be like in a cone, right? You think of it this way, that you have a circular disc somewhere, and you're watching it from some distance. So when you take those rays from let's say the perimeter or the circumference of the circle, so you will have this conical object that will be, you can imagine that in space you have a conical object. All the rays from the periphery are reaching you. So the
Yes.
angle of that cone, is what is d omega.
Yes, sir.
Okay. It need not, by the way, it need not be a cone. I'm taking cone just as an example because the area might be an irregular object. It may not be a circle.
Yes, sir.
Okay, but whatever, if you connect the rays, I mean, if you connect all the rays coming from the perimeter to the point where you are viewing that area from, then that angle in that, the angle covered by all those rays is what is d omega, the total angle. Okay, the circumferential angle, if you want to say it.
And
The
and
circumferential.
that angle is measured by which about which axis or plane?
No, it is being measured but from the observer. So you are an observer sitting here. You are an observer sitting here, let's say, at this point. It's not being
So
measured about the
so
plane.
as in 2D case, right? We have two rays,
Yes.
right? So we can
In
measure
2D we
one.
have two. In 2D we have two.
Yes, so
In
we can
3D we
make
would have
measure.
infinite.
We can measure angle of one ray with respect to another ray in case of 2D.
Right. Yes.
So I just want to ask that what about in 3D?
So in 3D you can imagine, okay, in 3D you can imagine that you start at some point. Let's say I am going to start at some point here. Okay, from this ray, let's say.
Yes, sir.
And I go all the way around until I come back to the same point.
Yes, sir.
Okay, so then the angle that is why I've drawn this d omega as a circular arc, which is, it's difficult to see. I mean, but it's not circular, but it's circular if you go in this if you're watching from this direction. If you're watching from
If
this
we make
direction,
like this, then that will be 360, right?
if you make what?
If we measure like this,
No, no, but
uh,
that is not. So what I'm saying is that it is not 360. We are not measuring it that way. We are saying this because this actually angle can have a larger. So think of this is an arc. I have made this circle just to say that this is the portion of that angle. Actually, it is not 360. We are not measuring it like in terms of circular angles, like in terms of radians. That's why I said that this is actually an angle which you are looking in a three-dimensional space. So this angle can be larger. Think of it this way, that if I open this, if the area was maybe slightly larger, let's say this area was maybe this size, then the d omega will actually new one will be this one, something like this. So it is not 360, then it becomes 360 throughout. I'm saying that now the cone is opening up.
Yes, sir. Yes, sir.
Okay, so it is not 360, it is not 2 pi, it is not 2 pi.
Yes,
Okay,
sir. Yes.
yeah, so it is that solid angle. That's why I said it's a solid angle. It's not the regular curvilinear angle that we are so used to dealing with in two-dimensional coordinate geometry. Okay, so that is a solid angle that we will be dealing with. So let me introduce. So remember, the units of this will be radians, and I'll show you one example of how the solid angle can be computed. So we're coming there now. So let's look at the fourth concept, which is of radiation intensity. And to define radiation intensity, I need to first define the coordinate system and what would be the solid angle measured in a spherical coordinate system. So what we know is that quite clearly, each surface responds to radiation, and it depends on the direction from which the radiation is either coming or it's going. I mean, the surface may be either receiving radiation or it may be emitting radiation. So we try and quantify that dependence in terms of radiation intensity. And to explain this idea, let me take a small surface. Okay, a small surface, maybe dA1. Okay, a flat surface which has a unit normal. Let me draw that normal in some direction. That is a unit normal on the surface. In three-dimensional coordinate system, you remember the three-dimensional coordinate system will work in a specific way. Let's say so we will have maybe the coordinate system work in a very certain way, which I'm just going to use as guidelines here. So let me say the z direction is actually aligned to the normal vector for now. I mean, that is typically the terminology that is used in radiation, and it's implicit. We don't say it very clearly, but I'm just saying. Let's say for starters, the z direction is along the normal direction. So let's say we take a coordinate at a distance r, some point at a distance r at some angle phi and some angle theta. So what we will have is, let's say I take some point. Let me use a very specific color because this may actually mess up the entire diagram. Let's say we take a point at some distance r, which is, let's say, at some angle phi and some angle theta in the spherical coordinate system. And let me now increase, let me take a differential increment in both theta and phi in terms of direction. So let's say if I increase in theta, I will have a small increment d theta, and if I increase in phi, I'll have small increment d phi. So the system would actually be something like this. So we'll have this angle as d phi. I hope it is visible. Okay. What I'm going to do is I'm going to connect these distances in terms of the radius r. So since r is fixed, let me draw a slice. Okay, let me draw a slice, and I think I may have messed up here a little bit, but anyway, let me draw a slice which sort of joins here, and let me also draw another slice which goes something like that. So we take a small element of size d phi, and then also a small element in terms of theta. Now remember that theta would basically mean that you have a projection of this r on the z axis. And then if I take a small element d theta, in terms of increasing the angle, it would mean that the new point would actually be slightly shifted. So we'll have at this, with this point as a center, I'm going to now have a small increment in angle that gives me d theta. Did I? Oh no, sorry, I made a mistake now. Sorry. So I have d r sine theta, and then we have a d theta. So yeah, so I can draw it. Just give me 1 second. Let me just work this out so that I have done it in the right way. So we have theta, d theta would be somewhere here. So we'll have an element which I've drawn now very foolishly, a small element. So this is d theta increment, and then in terms of the distance, we're looking at, let's say, this area in the three-dimensional spherical system. So this element that we're looking at actually has some very specific dimensions. For instance, this length of the slice is actually going to be r times sine theta d phi, because this length here, as I was saying, is actually r sine theta, because theta is being measured from that side. And then this length here, because we are using r as a radius, so this becomes r d theta, this length, the rectangular length, I should say. So we're looking at this element, which is sort of like dan from, let's say, in point da1. So when we talk about solid angle, let's say in the spherical system, we're talking about we're talking about viewing this point dan, which is on that slice at a distance r, but in the direction theta and phi. So we can talk about d, or rather the solid angle, I should say, d omega. As I said, was dan, the area which we are viewing versus the distance square from where we are viewing it. Now, the area, now this elemental area can be written in terms of d theta and d phi. So for instance, this will be r d theta, r sine theta, d phi, being taking that as a rectangle because it's a small area, versus the distance square. And so d omega in spherical systems, as we will be using throughout now, will be sine theta d theta d phi. That's the smallest or the elemental solid angle that we will tackle when we do calculations on a sphere. And there's a reason why I was saying that I will explain why we do it, where we'll do calculations on a sphere, because radiation typically is a phenomena that has a certain spherical symmetry. So it goes, radially out. So we will talk about, so that is, if it goes radially out, then spherical coordinate system becomes a most suitable coordinate system to tackle these quantities. Okay, so what I was saying is d omega here is actually sort of this angle, uh, which is, let me draw by white. So it is sort of like, if I join this point to all the corners of this area, then it is this angle, which is d omega. It is this angle, which is d omega, which is the angle which is formed by this area when viewing from that point on the surface. Okay. So now when we are, the reason I defined this is because we are now going to define what is a radiation intensity. So radiation intensity has a very specific definition, and this is a slightly long definition to explain. But what we're going to do is we're going to try and look at how emission from area DA1 sort of goes through DAN, or what amount of radiation is intercepted by an observer sitting at, let's say, this point at a distance r and in a direction theta comma phi, okay, and at a given wavelength. So say dq is the amount of radiant energy that is sort of, that is passing through DAN, that started from DA1, of course. So then we can write a quantity which is called as spectral intensity, which I'm going to write as similar to the way your book writes, as I lambda E. And I'll tell you what these symbols are for a given wavelength, for a given direction, which is given by theta comma phi. So spectral intensity, these in all of radiation analysis, these subscripts will actually denote dependence and also a process. So for instance, this subscript lambda denotes there is spectral dependence, as I said, wavelength dependence. And this subscript E denotes that we are dealing with emission. We're not dealing with something else, we're just dealing with the solid, emitting radiation. So we can write that uh, the spectral radiation or spectral intensity for the wavelength lambda in the direction theta comma phi is given as the amount of radiant energy passing through DAN, which is dq, versus or divided by the area of this surface, which is DA1, area of DA1 as seen from DAN. Now, when we say area DA1 as seen from DAN, we're saying that as you see from that point, the surface will not look in its entirety. It would not appear as DA1. It would actually appear as a projection of DA1. It would appear smaller. If you look normally, if you look right in the normal direction, then you see DA1 as a large area. But as you go in any direction, you will see that this area, and you see this area, you will see that it is becoming smaller. Okay, because it's basically the area you're at from a perspective, you actually don't see the entire, dimensions. So we will look at in terms of the intensity is defined in terms of the amount of radiation energy passing through that point versus the projected area, which is going to be dA1 cosine theta. And let me also show why it's dA1 cosine theta. So say we have this area again, dA1, and I'm looking at some direction, from some direction, which is, let's say, the normal vector is here, and we are looking as an observer, we're looking from there. So this is normal, and this is, let's say, angle theta. So now what I'm going to see from this direction is, if I look at just the edges of this area, what I would see will be this area. So here, 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 here. So even though dA1 was a large area, I'm going to see a smaller area in that direction. So this projection, now you can see, would be dA1 cosine of theta, where theta is again the same zenith angle, the altitude angle. So we have I lambda E to be dq by dA1 cosine theta per unit solid angle, which I'm going to write as d omega, about that point, and per unit wavelength interval about that point, about that wavelength lambda. So we define spectral intensity in terms of the amount of energy leaving versus the projected area, versus, of course, by the solid angle about that point and by the wavelength interval about that point. So to just to explain, let me write this in a sentence so that you can remember. I don't know, maybe it would be hard to otherwise understand. So we're defining spectral intensity as the rate of radiant energy emitted at the wavelength lambda in the theta phi direction per unit area, which is normal, uh, per unit area of the emitting surface, which is normal to this direction. So the direction which is theta phi, and per unit solid angle, which is d omega per unit wavelength interval, which is d lambda. So that is how we will define the spectral intensity of radiation. So there are multiple dependencies. There is the direction dependence. There is a dependence of solid angle. So what is the amount of the area? Solid angle basically is telling you how much is going in that direction. In that, how much is captured in that cone. And d lambda is because it's per unit wavelength. It is saying that about lambda, how much more is going. Very similar to how we do it in quantum mechanics. And of course radiation. Much of the radiative theory actually comes from quantum mechanics. Now, the units of this intensity are watt per meter square per micron per solid angle. So it would be watt per meter square micron meter, because microns would be the micrometer would be the common unit that we will use for wavelength, and steradians, because that is the unit of the solid angle d omega. But keep this in mind that this idea of where you are seeing that area from will actually matter a lot, because this will determine, and I'll take one example today just to show you what that really means. So a numerical example before the class ends today to show you how this solid angle matters. Now let me the same thing we can write. I mean, we can rearrange this equation that we have defined for spectral intensity. We can rearrange this equation and write that dq by d lambda would actually become equal to I lambda e of lambda theta phi d a1 cosine theta d omega. And dq d lambda is also called as dq with subscript lambda, which is called as spectral radiation rate. So using the spectral radiation rate, we can then calculate what is the spectral radiation flux in that sense, because this is still a quantity which has units of watt per micron. What we are more interested is in quantities which are related to flux or per unit area. So we can write dq lambda by da1 to be I lambda e lambda theta phi cosine theta d omega. And now remember, d omega is going to be sine theta d theta d phi, and this is called as spectral radiation flux, which is the flux per unit area of the radiating surface da1. Okay, so it's a flux corresponding to this area which is radiating in a specific theta phi direction, or at a given wavelength lambda. Now, if I have to calculate that, and sorry, so what is it? So this is second symbol for this. This is sometimes written as dq lambda double dash, again to define that this is the flux. So if I'm interested in knowing how much flux is radiating out from a body, let's say some area, in all directions. So far we've looked at only one direction, which is theta phi direction. If I'm interested in knowing how much is this body radiating in all directions, so we can go back to the same thing that we have done earlier, which is for in spherical coordinates. So let's say we have the area dA1 sitting on a somewhere, and let's say again we have the normal vector aligned in a certain way. So what I'm going to do is I'm going to define a hypothetical hemisphere about this point. So hypothetical hemisphere would mean that if we define a hypothetical hemisphere, we'll have something like about this area dA1, and I'm interested in knowing only how much flux is leaving. I'm not interested in how much is being received or at what distance is it being received. That is not important right now. How much flux is leaving from this body in all directions. So there I can again go back to the same idea that at a distance phi we take some. So let's say at a distance phi here we take an element d phi. Okay, and so that basically goes something like that, like a slice of a, I don't know, a lemon if you want to think of it, or a watermelon. And at an altitude of theta, so let me say theta is measured here, we take an element d theta. So the intersection of these lines is what is giving me this area DAN on that hypothetical hemisphere. So I'm going to calculate how much is going through one area, which I have already defined as dq lambda double dash. And to calculate the total hemispherical or the total flux over this hemisphere, I would integrate over all such areas above the hemisphere. Now, I'm using a term very loosely here, or I'm not even telling you why I'm saying hemisphere again and again. Now, the reason I'm using hemisphere in this problem is because, as I said, radiation is a surface phenomena. So if you consider any solid, any irregular shaped body, it doesn't matter if it's a sphere or, if it's a regular geometry or whatever it is. As I said, the radiation is a surface phenomena. What it means is that if you take any elemental area on this surface, which is, let's say, dA, then the normal vector is of course pointing outwards towards the medium or towards a other body where it's radiating. So anything to this side of this body, anything on this side is actually internal to the body, so that is not radiating any energy. So we are going to be looking at radiation leaving this body, and that only can happen in one direction, so in one half of the sphere, which is the hemisphere. So in radiation analysis, we only deal with hemispherical quantities. Okay, we only deal with, because radiation is going to go from dA1, and dA1 is going to be part of some larger body. It is not just that this body is radiating. This is a small element I've taken on some large surface. So we will have to integrate over all such DAs, in a body, to be able to calculate what is the total radiation leaving a surface. So keep that in mind, that hemispherical or hemisphere has a whole meaning in radiation analysis, because we are only dealing with a surface phenomena of radiation as a surface phenomena, and that is only going to be in one direction, not in both directions. Don't think of dA1 as a surface which is also radiating from the underside. I mean, if that was true, then of course we would have to. But as I said, even a body which is radiating from the other side, even if it's a plate, for instance, that plate has a finite thickness. And so what is going on down is not the same as what is leaving from the top surface, because the radiation is, as I said, is from going from the surface only. So you can imagine that the surface is a very thin layer. So radiation is going up from the top surface, and you have to do the bottom surface analysis separately, not as part of one complete analysis. So this is a heavy concept. I understand if you do not understand it right now, but hopefully by the next few lectures we will have a better understanding. Hopefully you will understand what I'm trying to say when I take a few examples of this. Okay, so when I say that we have to take this, yeah.
In the spectral radiation flux, you have taken dq lambda by dA1, like a bit above.
Yeah.
So, like as we have observed in this, like we took the flux passing through dN, so we should take the projected area dA1 cos theta for the flux, rather than taking the total area.
No, so we've taken that. In fact, so you see the cos theta is still there. Do you see this?
Yes, sir.
I'm not. So if I had defined, if I had taken cos theta down there, then the question, what you are saying is actually valid, but we are still keeping the direction there. The projected area direction. So what I'm saying is this area, this total radiation flux is per unit area of this surface, of this dA1. It is not per unit area. It's not per unit projected area.
Okay.
Okay. It's not per unit projected area. It's per unit area.
Yes, sir. Got it.
So you can imagine, yeah. So you can imagine that as I go down, this is good. At least we have a lively discussion today. So you can imagine that if you go down on this area, so see, if you are standing here, let's say on the top, then you would see the maximum possible flux, and that is understandable, right? Because you are seeing the entire area.
Yes, sir.
But as you go down, if you go to this point, which is on the rightmost point, there you don't expect to see any radiation, any flux.
Yes, sir.
Okay, so that is cos theta is actually accounting for that quantity now, because there cos theta will be 0 because theta will be 90 or pi by 2.
And
Okay,
one more thing.
so yeah.
So like you said, like in case of a plate which radiates from both above and top, so like if a plate radiates from the below, so will there be an interference of radiation, like the below radiation from the
No,
above plate and
no,
up?
no. Because see, remember, even a plate which is thin still has some finite thickness, and we are saying radiation is sort of, surface radiation is sort of a phenomena which happens only within a micron thickness of the surface. So you cannot have a surface which is, I mean, any plate that you deal with be maybe a few millimeters thick, let's say. So even then you are very far away from the other surface.
Yes, sir.
Okay, so what is radiating in one direction is actually only going in this, on above it. It cannot start going, so we're not taking that it's leaking down. Radiation is only going to go radially in those directions.
Yes.
Okay, so very similar to this, that if you take 2 points on this surface, one on the top and one on the bottom, the radiation leaving here will only be confined to this plane, below this plane, and radiation going from here will be confined to plane which is above this surface. So these two can never interfere that way.
Yes, sir.
Of course, if you go here, I mean, if you go to the edges, then it's a problem. But these are issues that we cannot tackle in a very simplified radiation course that we're doing right now in a few lectures. Okay, end effects, side effects, end effects are very difficult to manage otherwise. But if you look at plane surfaces, only planes, then we won't have to worry about this.
Thank you, sir.
Okay. So what was I saying? Yeah. So we can now calculate what would be the total radiation flux leaving this surface dA1 above in that hemisphere. So we can define what is called as basically what we can do is we can integrate this dq lambda double dash over the entire hemisphere to get q dash or q double dash lambda. So we can write q double dash lambda, which is the total radiation flux or total spectral, I should say, because lambda is still there. Total spectral radiation flux. This will be integral over the hemisphere. So integral 0 to 2 pi, which is the limit for phi, integral 0 to pi by 2, which is the limit for theta. Now remember, it's hemisphere, so theta can only go from 0 to pi by 2. Okay, of I lambda e lambda theta phi into integrate that equation which has cosine theta sine theta. So we'll have cosine theta sine theta d theta d phi. That would be the total spectral radiation flux leaving this body over the hemisphere. And interestingly, because that question about the solid angle was asked earlier, let's just look at what is a solid angle, of a hemisphere, which I'm assuming you would have guessed. If you're looking at the hemisphere, let's say this is a hemisphere, and you're looking at this hemisphere from some point, maybe down here, some point here, or even above, it doesn't matter. When you look at the hemisphere from some point, which is normal to the mid plane, what do you expect? What would you see? It's easy to see that what you will see is this area, or this, what you will only see this is this circular area, because that is the projected area of that hemisphere. So that actually has an area of 2 pi. I mean, the angle is 2 pi. So we can calculate d omega, let's say over the hemisphere, which will be integral 0 to 2 pi, 0 to pi by 2 of sine theta d theta d phi. So d phi is anyway integrates to 2 pi. Sine theta d theta will integrate to minus cosine theta over the limits of 0 to pi by 2. So that just becomes 1. So we get 2 pi stay radians. So that is a solid angle associated with a hemisphere. Now, from the total spectral radiation flux, we can also calculate the total flux, which accounts for all, or which accounts for radiation of all wavelengths. So total flux, which is q double dash, would just be an integral of q double dash lambda over all wavelengths, and all wavelengths would mean that we go from 0 to infinity, or in that electromagnetic spectrum. So we integrate over all wavelengths to get what would be the total flux, which is over all wavelengths, not just one. I mean, earlier we wrote it for only one wavelength. Now we are saying it's for all wavelengths. Let me see. Okay. So these quantities you will see very commonly now when we talk about radiation. Okay, we'll use these kinds of integrals or define, use intensity to determine different fluxes very commonly. I have so far looked at emission. Now for emission, we don't define just Q as a variable of interest. We define E as a variable of interest. So we define what is called as spectral hemispherical emissive power. So if it's emission, I will always use a symbol capital E to denote emission, which is going to, and since it's spectral, I'm going to write a subscript lambda, that it's spectral, to denote this is spectral emissive power. So this has units of watt per meter square per micron. And this is the same as what we have defined as the spectral radiation flux. So this will be again 0 to 2 pi, 0 to pi by 2. If you're dealing with intensity of emission, I lambda e, which is emission intensity, lambda theta phi cosine theta sine theta d theta d phi. That is a spectral hemispherical emissive power. And if you integrate that over all wavelengths, so for instance, if I do integral E lambda d lambda over all wavelengths, we will call this as the variable E, which is going to be is going to have units of watt per meter square now, and it's going to be called this total hemispherical emissive power. So when we say total, we are dealing with, or rather when we say spectral, we're dealing with radiation quantities which are still wavelength dependent. And when you talk about total, we are saying quantities which have been averaged over all directions and averaged over, or rather have contribution from all wavelengths, not just one wavelength. So this we can also write in terms of
Sir,
triple integrals. Yeah,
sir, can you scroll up?
yeah, just 1 second. Sure.
Sir,
Till how far?
sir, shouldn't the integral for E would be with should it be with respect to dA as well?
Should it be with respect to?
dA, dA1. Isn't
You mean E
E
lambda?
lambda same as flux?
So this is still a flux. So this is so. By the way, it's emissive power. It doesn't mean that we have integrated over. Okay, I understand. You were saying this is. It says it's. I think what you're saying is this is power, but it has has units of watt per meter square. Is that the confusion?
Yes, sir. Like, isn't this the same as spectral flux?
It
This
is. No,
expression.
it's not the same as spectral flux. It is not the same as spectral flux. It is the same as total flux.
Okay.
Not
Yes.
spectral. Because that dependence is now gone. The lambda dependence is gone.
Yes, sir. Yes.
Okay, but it's a valid point. I also don't know historically, certain way things are written in in a certain way. So even though it says it's power, the units are still written in terms of watt per meter square, because we don't consider the area at this point. Quantities are defined always per unit area. Okay, when you go to area, because it depends on, as you will see, bodies have complicated shapes. So when we write in terms of area, you need to know the entire, you need to integrate these quantities over the entire area, and that can be slightly tedious, so I'm not going there yet. Okay, but we will deal with per unit area quantities, which is far easier. That if you know that per unit area, this is the amount of radiation that it is emitting. And we will only apply these things to simple geometries. For instance, a plane slab, when you have a plane slab radiating, you know that the area is, the same thing will happen at every given location. And even if it's a spherical or a cylindrical system, even then you know that, the area element is the same everywhere. So then multiplying by the total area is easy. You get the entire, the actual power. But I don't have a great answer for saying that, why we still write power and have this watt per meter square. There is, it just historically it has stuck, and it has been carried over. There's no other answer for that. Okay, so I was saying that total hemispherical emissive power would then be, because we have this integral over wavelength as well, so we can then write this as I lambda E of lambda theta phi cosine theta sine theta d phi d lambda. So that would be the total uh, hemispherical emissive power in its full glory, if you want to say. Now, because we're dealing with total quantities, okay, and we are also dealing with, when we deal with emissive power, we sort of know that we're dealing with the hemisphere itself. So frequently you may see in many, in fact even in your own book, this term hemispherical would be dropped from these quantities. Okay, they will just say it's spectral emissive power, or they will say it's just total emissive power. So you should know that hemispherical sort of then becomes implied in the statement itself. Then when they say that it's spectral emissive power, because it's over all directions, so hemispherical sort of is redundant. We don't need to keep using the word to specify this variable of interest. Okay, so and the same with total emissive power. When you say total emissive power, we sort of know that we're dealing with all directions, all wavelengths is of course is already gone, because we don't talk about spectral anymore. But total would mean that we have considered all directions in the geometry. Okay, so now we sort of do a lot of radiation calculations are extremely complex, are difficult in that sense, but sort of we make some assumptions to simplify our calculations. So one of the assumptions that is made in many engineering surfaces that we deal with this concept of a diffuse emitter. And a diffuse emitter is one which sort of has where the intensity is not direction dependent. So diffuse emitter would be one in which the radiation intensity, which is I lambda e lambda, lambda theta phi, is only a function of lambda. That there is no direction dependence. So that kind of assumption, if we make, then it's easy to see that E lambda, for example, the spectral emissive power, and I'm dropping the term hemispherical now intentionally. So E lambda of lambda would just be, if you write in terms of the angles, right? It was 0 to 2 pi, 0 to pi by 2, I lambda E. Now, because lambda E is only a function of lambda, so we have cosine theta, sine theta, d phi, and that if you integrate, because remember d phi will give you 2 pi, and cosine theta sine theta d theta is an easy integral, because if you take sine theta to be, let's say, some variable m, then cosine theta d theta becomes dm, right? So that becomes just an integral of in that sense mdm. So what you will get is I lambda e into 2 pi into half, which becomes pi I lambda e. So a diffuse emitter will have a very simple linear relationship between the spectral emissive power and the radiation intensity, and the constant and the factor of this proportionality is pi. And similarly, if I want to write the total emissive power for the same diffuse emitter case, we can say this is going to be 0 to infinity. I, by the way, it would be E lambda d lambda. So I can write this as pi I lambda e d lambda, which is written as pi times IE, or the intensity of emission. So where IE becomes integral E lambda E over all lambda. So E lambda I lambda E d lambda is the value of IE. So this is total intensity of emitted radiation. So that includes all wavelengths in the radiation. So how much time do we have? Yeah, we still have time. So maybe let me now take this example just to illustrate the idea of the solid angle. Okay, so there is this, I'm not inventing an example here. I'm just taking one from your book, hoping that maybe you will revisit and see this carefully. So the example is sort of goes like this. So let's say we have an area A1, which is about 10 is to minus 3 meters square. And we have two areas in the vicinity of A1, and A1 is emitting diffusively. So A1 emits diffusively, which means that there is no directional dependence of the radiation intensity. Okay, say we have another area A3, or two areas in the problem. Okay, one is here and say one is here. So this is, say, let's say A2, this is A3. So they are at the same distance. Let's say if I want to draw from the normal, let's say this has a normal vector here, and these two have the same normal vector. So let's say this distance r is 0.5 meters, and this distance is also r, which is 0.5 meters. We know the orientation, so we know that this angle is 60 degrees. So the area A2 is sort of at an angle of 60 degrees from A1. A3 is right above A1. Okay, A2 and A3 also have the same values, which is 10 to the power minus 3 meters square. And so the question sort of goes like this, that first of all, calculate the solid angle subtended by, so let me write this, calculate the solid angles, or the solid angle subtended by surfaces 2 and 3 at or when viewed from 1. So when you are an observer sitting on 1, what would be the solid angle subtended by these two surfaces? So I'll make an assumption here to justify the way I'm going to solve this or calculate this. Let's say, I mean, we not say, but rather if we compare the A ratio, let's say AJ, with J is either 2 or 3 versus R square. So I can already see that AJ by R square is a number which is much, much less than 1, because the areas are very small as compared to the distance at which we see them. So I can consider that for an observer sitting on point on the surface 1, this surface is actually like an elemental surface. A2 and A3 are elemental surfaces, so all points on this surface are at an equal distance. Okay, are at an equal distance for me. So I'm not going to do a total integration. I would rather use a simple elemental calculation that I have done for the in the earlier part where we defined this angle d omega. So using this, say if I want to calculate omega 3(1), which is an easier angle. 3 is the surface right above surface 1. Okay. So if in case you want to see the schematic and then do the calculation, let me try and put them on the same screen. So let's say we want to calculate omega 3(1). So omega 3(1) is the solid angle subtended by surface 3 when viewed from surface 1. So that would be the angle, or rather the area when projected along that direction. Remember, you're watching from A1. So when you project, because the normals are the same, it's right above this. So we'll have A3 into cosine of 0 degree by R square as the area when you see from A1. So that you can easily calculate would be now just 10 raised to minus 3 by 0.5 square. So that becomes 4 into 10 to the power minus 3 steradians. Okay, as from a point on surface A1, I can see the entire area A3. It is not going to be some projection of A3. Please remember this. Now, what about omega 2(1)? Now, this will be A2 into some projection, let's say, of A2 by R square. Now, what would be the projection? This is the difficult part that some people may have maybe a hard time trying to figure out or trying to visualize. What would be the projection when you see area A2 from A1? What do you see the entire area A2, by the way? And these are, by the way, these are rays which are coming parallel to the line connecting A1 and A2. So this line that I've drawn here, let me draw by maybe a dotted line now just to show. So we're going to see this sort of like parallel lines. So what you would actually see would be this area, right? The projection of A2. So what is the projection of A2? The projection of A2 is what I'm writing is A2 cosine theta 2. And which theta 2 is this? What would be theta 2 in this problem? Remember, this angle is 60 degrees here. So for simplicity, I can say this angle is 30 degrees. So what should be cosine theta 2? Yeah. Can somebody fill in the blanks here?
30 degree.
What should be? Yes, so that should be 30 degree. Because you will see projection along that 30 degree line. So this comes out to be about 3.46, 10 raised to minus 3 steradians. So that is a solid angle subtended by the two areas at when viewed from 1. When viewed from 1, that is more important. Now let's look at the second part. Now this is an application of what we have done with the intensity so far. Okay. So say second part of this question goes like this, that calculate the rate at which radiation emitted by surface 1 is intercepted by these two areas, is intercepted by surfaces 2 and 3. And to complete this question, let me also say this: the surface I said is emitting diffusively. So we are given the radiation intensity IN, which is the intensity along the normal direction of the surface A1. That is given as 7,000, let's say, watt per meter square per steradian, and per that is per steradian, and that is the intensity along that direction. It's emitting diffusively, so this is the total intensity now, because the wavelength dependence has also been accounted for. Now we are only looking, or rather per microns, per steradians, yeah, at this point. So it is actually already has a wavelength dependence included in it, or rather removed from it. So when I say normal, you will see IN, which is the normal radiation. We will typically talk about normal radiation in this form, that it is radiation in this direction from the surface along the normal. But because the surface is emitting diffusively, so we are saying it is emitting in the same factor everywhere. So along each point on that hemisphere, now, so it is emitting as 7,000 everywhere, because it's emitting diffusively, not because the normal intensity is given. So now I need to calculate how much is reaching these two surfaces, A2 and A3. So we can again do the surface 3 first. So say I want to write, let's say, Q, which is the amount of radiant energy leaving 1 but reaching 3, which is 3 is a surface right above it. So that should be in terms of the intensity and in terms of areas and in terms of solid angle. So let's say this is going to be I lambda, or rather IN in this case, because that is, it's a diffuse surface. So IN into the area, which is, remember if you look at, let me go back to the integral again. There is a total flux spectral, yeah. So if you look at this integral, which is per unit area of 1 anyway, but if you look at this integral, you see that we have to have, it considers this cosine theta dependence in it with a d omega dependence. So this part, which I very conveniently wrote it here, this was actually d omega, and the cosine theta is not part of the solid angle. Cosine theta was actually separate from the solid angle. So we will write this as the radiant energy as In times cosine of the angle, which is, in that direction. So in this case, I know that the surface 3 is along the normal direction only. So that is cosine 0 degree into the solid angle, which is angle when viewed from 1. So I can write this as, I don't know, did I write? Yeah, omega 3(1). So that would be the amount of radiant energy reaching surface 3 when leaving from 1. Now you can plug in values and see that this is what, 7,000 cosine 0 is 1, and this was 4 into 10 to the power minus 3. Just 1 second. Did I mess up my unit somewhere? Oh yeah, into area. Sorry, I forgot about the area completely. That this is the total flux. So this is also into area. So we also need A1. So A1 was 10 to the power minus 3. So this becomes 28 10 to the power minus 3 watts of energy, or rate of energy reaching surface 3 from surface 1. And then if you look at Q1 to 2,
Sir,
which would be yeah.
so we're taking cos 0 degree because the emission is happening diffusively, right?
because the emission is
diffusively emission is
no,
diffusive.
we're not taking that, because we are saying we're taking it because if you look at the line connecting this to this, so at this point, right, if you're looking from 3, this surface, it actually has so the normals are aligned.
Yes sir, yes sir.
The normals are aligned for the two surfaces, so there is an angle of 0 degree between the normals. But so is not the case when you look at 2 and 1. Okay, remember the zenith, the theta
Yeah.
angle is when you're viewing from that altitude. So right, the theta is being measured in a certain way. So same thing would actually happen now here. If you look at q1 to 2, so we'll have in cosine theta 2 into a1 into omega 21. Now in is of course 7,000, but what is cosine theta 2 now? Now this is not the same cosine theta 2 that I've written here, and I'm being a little shoddy in my symbols here. But when you're looking at surface, when you're looking at emission leaving from surface 1, this is emission leaving from surface 1. So how much is actually effectively leaving? Effectively, what is leaving is the projection of A1 along the direction. Right? So projection of A1 would mean that you have to take cosine of this angle 60 degree, because that is what surface 2 is going to see. It is not going to see the entire area again. That is what was this angle theta. Remember, if you, again, I'm going back to the very basic, the very starting of this lecture, when I said it is projection of the emitting area, dA1 cosine theta, right? So it is a projection of this area when viewed in a certain, from a certain direction. So we now have cosine theta 2 to be cosine of 60 degrees into area is anyway 10 is to minus 3 into whatever this was, I don't know, 3.46. Okay, 10 to the minus 3. So this, I don't know what is the number here for this calculation. This is about 12.1. So when we are viewing from that angle, then it becomes different. Now, I can just slightly change the problem and tell you, what if A1 was not flat in this way? Maybe it was inclined. It was looking at A2, and A2 was also inclined but looking at A1. So that basically means that A1 and it sort of becomes that A1 and A3 is, are like this, but I turn them around. So they still see each other. So the angle would still be 0 degrees, because the normals, they're seeing each other completely. But the projection comes in only when these areas have normal vectors which are at an angle to each other. When they are at an angle, then you know that these two areas cannot see each other completely. They will only see projections of each other. And because the intensity is defined in terms of projected area, so we use this cosine theta 2 here, which is or into A1, which is the projected area of A1, not the absolute area. Okay, so I'm going to stop here, but this is something that you need to maybe hear this lecture again, and please convince yourself that this is, the definitions are done in a certain way, and so they have to be followed in that manner. You need to remember that it is not so far as intuition as the definition that has to be followed. So projections can actually lead you into trouble if you don't follow what is being measured with respect to which direction. Okay, so I'll stop it here.